Right. Good afternoon and welcome to the first 2023 Iowa Learning Farms Conservation Webinar. For those new to the webinar series, welcome. For those that have been on many, welcome back. It's great to see so many folks online here to start the year off. And so I'm Matt Helmers with Iowa State University, Director of the Iowa Nutrient Research Center and Faculty Advisor with the Iowa Learning Farms program. And so really excited to welcome Dr. Keith Schilling, that's the State Geologist and Director of the Iowa Geological Survey, to talk to us today about floodplains as conservation opportunities. As always, I would encourage you to type any questions for Dr. Schilling into the chat box, and we can get those to him at the end of his talk. With that, the virtual floor is all yours, Keith.
Great. Thanks, Matt. Done this once before, and I'll do the same thing I did last time, which is probably overload the content for the amount of time. But, you know, there's always a balance to be had about, you know, more material or less and more discussion. I'm going for more. So there's a lot here. So thanks for the opportunity. Second title slide. And really the purpose here is to share some of the research that I've been doing over the last 20 years or so, and really making the case that floodplains are opportunities for conservation. Quick little plug about who I am and who I work for. I'm with the Iowa Geological Survey. We're a group of 11 or 12 folks here in Iowa City, located within the IIHR Hydroscience and Engineering umbrella. So welcome to visit anytime or interact with myself or any of our staff at any time. Well, we're familiar with alluvial corridors and river systems in Iowa, all floodplains, and all rivers and streams are underlain by sand and gravel deposits and alluvial corridors. So a typical cross-section might include a winding river, sand and gravel alluvium anchored in maybe a depth in glacial drift or in bedrock materials. These alluvial corridors have been very important in the history of Iowa. You know, our floodplains contain a lot of our societal activities, from farming in many cases, native vegetation and ecosystem corridors, and they're also the subject of a lot of urban development. All of our major rivers or our major cities are located on rivers and floodplains. So they're very important to Iowa's future sustainability in many ways. Now, given the level of activity that has occurred on floodplains across the state, I think it's important to first take a look at how floodplains are supposed to work. You know, here's a very cartoonish look of a floodplain, and that floodplain is essentially the width of the historic channel from bluff to bluff. It includes a lot of different features. And we're going to talk about several during the course of this presentation. But first, let's think about what a natural floodplain would look like. And some work that I've been involved with over the last bunch of years has been out at the Nature Conservancy's Land of the Swamp White Oak, which is a preserve that they own on the floodplain of the Cedar River. You can kind of see from the photo, it's in Muscatine County. Here's the Cedar River. This area in yellow here is the preserve. And these little dots here are monitoring wells that we put in that location in the TNC ground. Some things to think about how floodplains are supposed to work is that groundwater and surface water are closely linked in these environments. Okay, river stage goes up, groundwater level goes up. You can kind of see the close correlation here over a few years from water level or river stage and a center well, which is just a well in the floodplain. You see how closely correlated they are. Let's zoom into one peak on the hydrograph and say you know, from the river stage in blue to the water table level in red, there's a little bit of a lag, but clearly when the water stage goes up in the river, it brings the floodplain water table up with it. Okay, so they're very closely linked. What's interesting to note here in the red is these little squiggles that show up in the water table levels in the floodplain. This is due to plant water uptake of that shallow water table level that's only 2 or 3 feet, 4 feet down below ground surface. You can use this diurnal water table fluctuations to estimate plant evapotranspiration, because during the day, the plants are transpiring and moving water. Water is moving up into the tree, and we got water level decline. At night, those plant stomata close, and we got water table recovery at night. So you see this diurnal fluctuation. The difference between the night and the day from one day to the next is proportional to plant evapotranspiration. And if you summarize all this on the course of months and days across years, you get some estimate of how much water is being uptaken by the vegetation on this native floodplain. I should have noted that the Swamp White Oak location is this rare floodplain savanna with a lot of native savanna type or a lot of big swamp white oak trees, other native tree species with an understory of sedges and some other grasses and so forth. So it's a really beautiful location. But anyway, we're back to the diurnal water table fluctuations. You see that we can estimate how much water is being uptaken in this environment. A cool thing that we noted here is we put a dissolved oxygen sensor next to a big oak tree, a swamp white oak tree, and we saw this really interesting observation where the transpiration was out of phase with how diurnal dissolved oxygen was fluctuating. So it was quite interesting where transpiration and the dark black line would decrease on one end at during the nighttime. It would recover, and the opposite pattern was observed with the soil respiration and dissolved oxygen. So at nighttime, all the carbohydrates that were accumulated in leaves move into the roots, and it stimulated the bacteria at that point, and they consumed all the oxygen at nighttime. So it was interesting, out of phase. I believe we were probably the first one ever to see this activity. So I'm still into this, how floodplains are supposed to work. So bear with me. So how does the water quality in the floodplain compare to the Cedar River? Well, that is a pretty easy comparison to make. If you look at, for example, this is the box plot of Cedar River versus groundwater at the Swamp White Oak site. Cedar River, of course, has high nitrate concentrations. There's very little in the groundwater under this natural floodplain. All these variables were significantly different. So the river water, even though they're closely connected, the river water is very different from the floodplain groundwater. And if you add up all the ET that's going on, that occurs from mid-May to early October, that rates were about 4 to 7 millimeters a day. If you added them all up over that 150 hectare preserve, that preserve, essentially all the vegetation there was just from groundwater alone, was transpiring about 4 million liters of water per hectare per year, which is equivalent to a well that's pumping 300 gallons a minute at that location. So that's a lot of water uptake. And if you compare that or add into the nutrient concentrations in the groundwater that we saw, and said all of those nutrients were taken up by the vegetation in that environment, you can see that there's a significant accumulation of nutrients in that vegetation, including a couple of tons per year of carbon. So during non-flood periods, these floodplains are serving to process a lot of water and a lot of nutrients and storing it in their vegetation. So where does this water and nutrient processing occur in floodplains? Okay, coming back to our cartoon diagram, we've done a lot of work showing where all this activity occurs in this bar and swale topography, or I was calling it ridge and swale topography, and these meander scars. If you look at the Swamp White Oak Preserve, and I've color coded the LiDAR elevations to say green is low and the tans and pinks are high, you kind of see it has this kind of arc-shaped appearance as the floodplains are getting built in over time. And so if you look at the cross section from A to A prime there, you kind of see that if you went from one to the other, you're typically rising and falling and rising and falling subtly. You know, it's only a meter or so, but you have these ridges and you have these swales environment. We put monitoring wells in the ridges and in the swales and compared what the water quality was like in these two very kind of micro environments within the floodplain. And it occurs, what happened was that there are definite, very definitive spatial variations in a lot of parameters in really close proximity to each other in this floodplain groundwater that's overall extremely flat across the site, okay? Water tables are higher or deeper in this ridgy, the sandy ridge ridges because of it's just a little higher topography. But overall, you see big differences in dissolved oxygen, ORP, and so forth occurring in these two different environments. Are you in a sandy ridge or a silty swale? And if you kind of piece together this, and we did some geophysics and some spatial mapping, you can kind of identify where these biogeochemical hotspots are occurring in a natural floodplain environment. Okay, they typically occur in these fine textured or great organic rich swales where the water table and anaerobic, where they have anaerobic water quality. These are conditions favorable for denitrification. So there's a whole suite of studies out there showing how all these above ground processes are really patchy in floodplain environments. Well, what we showed was that groundwater is also very patchy in these floodplain environments, and most of the biogeochemical processing is occurring in the swales of these floodplain environments. So what about flooding? Here's your speaker standing out at one of our well locations during a minor flood in this case. So here's just the sequence of flooding and how this kind of emerges at the Swamp White Oak Preserve. This is in response to early 2008 flooding, because you know later in 2008 it was under 10 feet of water. You kind of see how if you just fill different elevations with different flood stages, you can kind of see how the flood water propagates into the site. The black dots are monitoring wells. So you kind of just see how the flood water encroaches in. And eventually you're left with a few islands. Quick little funny story. Peter Jacobson and I, who've been working out here for a long time, actually was out at the site on this very day at this elevation of water, kayaking or canoeing to our wells to get those sampled. Well, it turns out it's a lot harder to find locations when you're in the water above where your normal tracks are. You're essentially up in the trees. So believe me, it was really hard to navigate and know where you were at a site where you've been to a million times when you're above in the water. So as part of this floodwater process, when we put a YSI zone down the well, this zone measures levels, temperature, specific conductance, dissolved oxygen, pH, and ORP. Every one of these little examples I'm showing here is another study. So believe me, I'm hitting the high points of a lot of different activities. But we put this zone down in the well during the 2008 period, which included these massive floods. And again, I could dig into great detail on all this, how this viewed from April to October in 2008. What's clear from all this interaction of the surface water above the groundwater in these systems is how dynamic this is. For example, dissolved oxygen rising and falling, this ORP that shows the biological activity consuming all this floodwater pulse of nutrients and dissolved oxygen, rapidly changing all the time, especially in the silty wells, which is the low wells, which are the red lines here. So this is a very dynamic system when floodwater comes in and encroaches. If you look at water quality in the floodwaters versus the floodplain, it's pretty clear that like all floodwaters in Iowa, concentrations are, 2 to 6 milligrams per liter. We were able to get out and sample that well during floods on many occasions. And it looked like the groundwater at the site, even though all that flood water eventually infiltrates into the groundwater, the flood water was much higher than what was ever measured in floodplain groundwater. So that's how floodplains are supposed to work. Let's transition a little bit about farming on floodplains, because clearly that's a major activity that occurs. So why do producers farm on these floodplains that are known to flood? Well, it's flat, it's relatively easy to farm. There's high organic matter soils, there's abundant soil moisture. We saw how the water table was very shallow in these systems. And the farm programs provide insurance, so it takes away, kind of removes the negative consequences. So farming is, given this, why not do it on floodplains? The soils themselves, these A horizons typically develop very quickly. Instead of eroding soils like you see in uplands, these are kind of accumulating soils from floodplain overbank deposits and so forth. So these tend to be very highly organic rich soils, again, with replenished by nutrients and high moisture content. So in droughts, these are probably the best yielding parts of a farm, are the floodplains. Well, farming floodplains also has some environmental consequences. This is actually a LiDAR image, or a colored, or a LiDAR, yeah, I guess we'll just say LiDAR image of this bar and swale topography of the Cedar River floodplain. You note how there's natural ridge and swale topography, and then you get this area here that's very flat. Well, this is an area that's been farmed. And with the Nature Conservancy's participation, we use that area to do a study of floodplain farming. Okay, this has historically been farmed. It was farmed again for our special study, and we put a series of wells in the crop area, under a kind of a reed canary grass dominated area, and in the woods. So network of wells in those three environments we monitored for a 3-year period. Cedar River flooding is shown by this black line. You can see that several times it got close to the flood stage, and in 2013, massive flooding occurred. The colored lines are the water tables measured in those 3 different environments. They all behaved the same, but during that last year, the flooding was just too severe and no crop was planted. They did some radishes and cover crops during 2013. So in addition to the levels, though, we measured quality. And what we saw was really kind of remarkable. So we had a soybean year in 2011, a corn year in 2012, and then this fallow year after the flooding. The soybean year had some phosphate applied. We had 2 different occurrences of nitrogen and side-dressed liquid N in the corn year. And then the fallow year, nothing except preventative planting. Well, the concentrations in the shallow water table were really pretty astounding, that we had nitrate concentrations in the fallow year with no fertilizer applications of 20 to 70 milligrams per liter, essentially the year after it was applied with fertilizer. So this says that there's a legacy perhaps of storage there in that nitrogen, and it was released during the floodwater encroachment. The second graph just shows an steady increase in specific conductance in the water table under the crop year, and during that same time, a decrease on the other 2 environments. So there's clearly a water table signal of water quality associated with floodplain farming that's not just in the current year. The current year of that corn application was 10 to 20, but it really showed up the following year during a floodwater pulse. So there's a legacy of floodplain farming with the corn rotation, and like a normal 2-year floodplain, in this case, we had crop failure 1 out of 3 years. So it's pretty consistent. That's how often you're going to see a 2-year floodplain perhaps have crop damages. So what other features of floodplains are noteworthy in terms of water and nutrient processing? Well, in a watershed scale, so now we're moving up beyond just the floodplain itself to comparing a floodplain to the uplands surrounding it. Here's just an inset map of Walnut Creek watershed, which is in the Neil Smith National Wildlife Preserve in Jasper County. Typical Iowa watershed. The black here is the floodplain materials, and then we have uplands and side slopes. But we see there, and we see everywhere we've looked at this, that there's really differences in water table behavior between the floodplains and the surrounding uplands. So the water tables typically fluctuate within a very narrow range, usually less than 2 meters, oftentimes less than 1 meter. So very wet, very shallow water tables. The uplands surrounding that typically have big variations in water table fluctuations over 3 to 4 meters. Okay, so big swings in water table in the uplands, very steady water tables in the floodplain. If you look at a cross section to a typical watershed, this is anything probably not on the Des Moines lobe. You see, oxidized loess and oxidized till, and a deeper core of the geology being unoxidized till. We see movement from the uplands across that interface down to the floodplain. Okay, and what happens here though is we get some recharge, vertical recharge to the water table in the uplands. We get a little bit more side slope runoff occurring, so lateral flow on the side slopes, and then concentrated recharge on the floodplain. If you add it all up over the course of a year or more, in the uplands, you might see about 24% of the annual precip showing up as groundwater recharge, less so on the side slopes, and you get a concentrated pulse of recharge occurring in the floodplains. Okay, it's a water table, highly receptive to recharge and also runoff discharge into the floodplain itself. So you get more concentrated recharge occurring in the floodplains. We did a similar study here in Clear Creek in eastern Iowa. We put wells in different representative environments of row crop, perennial vegetation, urban and suburban on floodplains, slopes, and uplands. And what we found, the same thing there as we saw in Walnut Creek, was that the floodplain that had this area of concentrated recharge occurring. Practically double what you'd see elsewhere in the watershed. So you get concentrated recharge, and if you crop in that areas, what you see is this translates to differences in nitrate loading. So the row crop in the upland, yeah, that's still not great at about 27 kilogram per hectare, but it was 40% higher in the floodplain because we had so much extra water movement through there. Okay, so in contrast, though, look at the different vegetation types here, suburban maybe with lawn fertilization and so forth, but overall much less from different land covers. But the point I want to make here is that with this concentrated recharge going on, we see concentrated nutrient loss also occurring in floodplains. We followed up some work in Walnut Creek with the study now looking at dissolved phosphorus, orthophosphorus in this case, and did the same thing. We looked at where was the phosphorus loss occurring and how did that relate to recharge? Well, the upland mass of phosphorus loss here at a much lower concentration compared to the floodplain mass loss, about triple the mass loss in the floodplains. We had higher concentrations and much more concentrated recharge. So the nutrient loss relates to both kind of subsurface aqueous nutrients, nitrate and dissolved orthophosphorus. So some perspective. We've done some work recently looking at the entire Mississippi River Basin, and among all natural infrastructure practices, we said, and divided them all up into all of our Huck 12s, you know, this smaller size watersheds. If you looked at all of Iowa's Huck 12s, there's 1,552 of them. How much row crop is occurring in floodplains? In this case, there was, in our analysis, there was nearly 8,000 square kilometers of floodplain or row crop in floodplains, and on average, it was 5.8%. But if you do a distribution plot of all the Huck 12 watersheds and how much of their watershed was in floodplains, it's clear that 10 to 20%, up to 20% of a watershed might be in a floodplain. So this is a significant area of land that occurs in a floodplain, but it's not all of it. Okay, so it's not, you know, it's a fraction of the watershed area. How does Iowa compare to other states with row crop and floodplains? It tends to be a little bit higher, to be honest with you. Iowa has slightly higher percentage of row crop land and floodplains in Huck 12s compared to a lot of our surrounding states, at least on the median wise and maybe the upper distribution. So let's look at an example of potential for opportunities for restoring some of this land in floodplains to take land out of production. We're looking at the English River, for example. In eastern Iowa, there's the map of the English River. There's Iowa City, Coralville right there. It's a typical Huck 4. Part of our Iowa Flood Center group and through work with the Iowa DNR mapped all of our floodplains across the state. So we now have flood inundation maps for floodplains from 2, 5, 10 up to 500-year occurrence intervals. Detailed maps makes for some great kind of comparisons you can make across here. So let's look at how much land in the English River floodplain might be in crop, in this case, on these different floodplain intervals. Well, for the English River example, half of the land in the 100-year floodplain is in crop. And 28% of the land in the 2-year floodplain is in crop, but this is only 3% of the watershed. So while there is land in crop production in floodplains, there's also at the two-year interval, not that much land. And you know, the thought is that this is a very low-hanging fruit possibility for floodplain restoration. They leach a lot of nutrients, particularly nitrate. They're subject to flooding once every 2 years on average, and it's not that much land. What do you think about restoring those two-year floodplain corridors? Using the some work that Calvin Walter and I did on the Raccoon River TMDL, we did a couple different scenarios of where restorations can occur. In this case, this is a kind of a amateurish map of the South Raccoon watershed. We kind of got the alluvial soil. So this is not the floodplain per se, it's just all the soils that are mapped with alluvium as approximation of floodplains. And we compared how much nutrient or nitrate reduction you can get if you restored all the highly erodible land, all the sloping cropland to croplands in the floodplains, okay? Again, every one of these is a separate talk, so there's a whole much detail I'm leaving out here. I want to get right to the point. With the two columns there, let's convert the row crop land on HEL ground, highly erodible land, to CRP, or let's convert row crop on alluvial soils to CRP. You can see how much of the row crop land was converted. It's a lot more on HEL ground. 36% compared to about 12% of alluvial soils. But the nitrate load reduction, we converted 36% of the land on HEL ground to CRP, we get a load reduction of about 28.8%. On the other hand, if we can convert about 12% of the row crop land on alluvial soils, we get a greater than 1% return, 100% return. We get 15.7% nitrate reduction. This is based on SWOT modeling, so there's some caveats in that case, but it looks like if we convert alluvial soils from row crop to CRP, we get up to a 1.7 times more nitrate load reduction than converting sloping ground to CRP. Something to think about. Some other work on floodplains that doesn't necessarily relate to what I've talked so far, but they are serious important floodplain features are oxbow lakes. We've done a lot of work recently looking at oxbow lakes as a INRC nutrient reduction practice. There's this study among follow-up work that we've done here showing that if you routed a drainage tile into an oxbow lake, you can expect to get some nitrate reduction benefits by this oxbow in itself. Taking the input load from the tile drainage and getting up to 44 to 47% of the nitrate reduced because of the processing that goes on in these oxbow lake kind of wetland environments. Cost of these are similar if you wanted to restore it as similar to a bioreactor or so forth at $10,000 or $15,000. But these oxbows also provide nutrient reduction benefits on floodplains. We've done other follow-up work in Eastern Iowa looking at what happens when we take an oxbow and restore it from filled depression to an oxbow lake next to a stream. In this case, the water in this oxbow only received overbank flooding and did not receive tile drainage. So the input load of nitrogen was very low relative, but it did the same thing. During a flood period, we put a Nitrotax sensor in this oxbow, and the nitrate concentrations in the oxbow decreased from 5 to less than 1 over a 3-week period after a flood pulse. So this oxbow was restored, but think about all the natural oxbows out on floodplains everywhere. They're all serving the same purpose. They get a floodwater pulse of nitrogen, nitrate, they will reduce it in short order very quickly. And lastly, I'd be negligent if I didn't comment on all the other benefits of floodplains. Okay, so apologize to all the natural resource biologists out there. I zeroed in right onto the hydrology and water quality. That's my specialty. But what are the other important functions of floodplains? Clearly, they provide a massive amount of floodwater storage. Okay, this picture would show floodwaters encroach into them. We saw from the work I presented how much of that water and nutrients can be processed by those environments. They dissipate the energy flood flows. So instead of the scouring energy in a channel, they dissipate that energy with surface roughness out in a floodplain, provide a massive amount of organic matter in the floodplain, and they contribute to improved fisheries. This is work from the Iowa DNR where they've out and seined in floodplains during a floodwater event. They actually tagged northern pike, and then they recovered those tagged fish out in the floodwaters of the Wapsie River. So these major fish species are migrating out of the floodwater in the floodplains or in floodwater, feeding and spawning and so forth. So there's a lot of other important functions of floodplains not covered here, but clearly there are a lot of benefits that accumulate in these environments. So wrapping up a whirlwind tour of floodplains as conservation targets, let's summarize, okay, a little bit. Floodplains with perennial vegetation, they utilize water and nutrients during both flooding and non-flood periods, okay? During non-flood periods, they are utilizing the water like a pumping well would up in these trees in this perennial vegetation. They're sequestering a lot of nutrients and carbon. During flood pulses, they process a lot of nutrients delivered with these pulses. They exhibit spatial heterogeneity, which is important for a lot of ecosystem functions. In this case, they have subsurface heterogeneity and lithology and water quality. And especially these swales are really hot spots for nutrient processing. Of course, they provide important ecosystem services for ecology, wildlife, fish, and hydrologic services. On the other hand, and they don't provide, or they don't constitute significant areas of watershed, as much as 10 to 20%. But unfortunately, many of our floodplains are cropped, and many of our 2-year floodplains are cropped. And these floodplains are sources of concentrated recharge and nutrient loss. And these agricultural nutrients that are leached in floodplains soils are stored and lost during vulnerable flooding and post-flood periods. So you could have a crop 1 year, and then that storage could occur, and the next year it floods, we get a massive release of nutrients based on the work that we've done in the Cedar River floodplain. So I'll just end here by saying that I mentioned earlier that floodplains, I believe, and colleagues and I believe, they're just the low-hanging fruit for conservation. We should think very seriously about removing some of our 2-year floodplains away from cropping into some sort of perennial vegetation to provide all these services that I've just chatted with you about. So with that, I'll end my presentation, be happy to take any questions. Oh, no, there's 2 more slides I just added today. And I'll let you finish that up, Matt, if you want.
I can handle that. If you you can take a drink of water, get ready for some questions. And for those that have questions, feel free to type those in. If you watch the webinar live today and want to earn a CCA CEU, send your name, the name you entered to watch the webinar, and your CCA number to Elena Whitaker. And that her email is alenaw@iastate.edu. Again, alenaw@iastate.edu, and do that by 5 o'clock today. And then put a plug in for the webinar next week. That we have Joe Otto, Director of Special Projects and Partnerships at Soil and Water Conservation Society, is going to talk about lake drainage in Iowa from 1880 to 1920. So for any history buffs, you will definitely want to tune in to that. Okay, we do have a few questions that have come in. I did have a question. This is, I'd take my prerogative as the moderator to ask the first question. For the Raccoon River example, what kind of on those alluvial soils were those all the alluvial soils? Was it like the 2-year or 100-year?
No, in that case, we kind of predated our ability to have that coverage. So we used the soil coverage, and where there was sandy soils in that environment, we called it alluvium.
Okay, cool. Thanks, Keith. Okay, first question here. If you can just clarify what ORP stands for.
Yeah, that's oxidation reduction potential. It's just really it's giving you an idea of kind of like the biogeochemical activity. And if it's positive, it tends to be higher DO. Negative, there's a lot of activity going a lot of electrons exchanging positions on a variety of different biogeochemical markers. So way too much to explain. But
okay, next one. How does stream bank work, such as changing a vertical bank to a more gradual slope, influence riparian hydrology and nutrient treatment?
That was almost a plant. This other work that it's a whole nother topic. There's a million different ways to go, but there's in these steep vertical banks, what you see oftentimes is that the near bank environment is largely disconnected from the surface and groundwater interaction. You might have very extremely dry conditions above where you expect to see saturated conditions, because the banks are high and dry relative to the surface water in the channel. So you'd get, you could plant an oak tree next to an incised bank, and it's going to behave just like an upland in many cases, because it's dewatered. On the other hand, if you gradually shape those and make them a little more natural shape on those banks, you're going to get a lot more surface and water connectivity in the riparian zone and get more exchange that way. So there is a big difference between steeply vertical banks versus a gradual bank in terms of the interaction of the floodplain and riparian zone, in particular, groundwater and vegetation with the surface water.
Does the quality of the floodplain vegetation change the value proposition from your perspective?
From my perspective, probably not a lot. I mean, for example, on the study I shared, we had canary grass versus trees. And yeah, the trees were, perhaps removed some more water. I mean, you get a dense stand of canary grass and that's pumping out some serious water too. The difference was really perennial cover versus a crop cover. I think there's be a ton of differences in terms of above ground, biomass, ecosystem services, and all this sort of activity. But subsurface wise and the interaction with water quality, it's probably mostly perennial versus annual differences.
The floodplains you mentioned in this talk seem to all be active floodplains. This person says, I assume that reconnecting floodplains that have been disconnected would provide some benefits as well.
Sure. Yep. And if disconnected means in this case, like it's levied, clearly all the conditions on the other side of the levee, on the land side of the levee, are available and ready to be used the minute it sees floodwater. Now, if it's disconnected because the channel's incised and it never reaches the floodplain, or it's a terrace, we're probably moving into other territory at that point. But if we could reconnect floodplains, especially in leveed areas, to gain some of these services, I think that's that would be a real win. If the streams have been so degraded or downcut and leaving the floodplains high and dry, essentially making new terraces, we've got probably larger issues to deal with at that point.
Since you've been involved with a few of the oxbow restorations, any information on what programs are available for small oxbow restoration along creeks, or maybe who to contact?
I think you might be better that one, Matt. I'm just a science guy here.
Yeah. Yeah, no. There's even well, Fish and Wildlife has put some of those in, and the Nature Conservancy has been heavily involved with some of the multi-purpose oxbow restorations up in north central Iowa, at least. So
yeah, but there are programs available, I think,
yeah,
increasingly available to do this.
All right. There is, friendly reminder. We got a forester on. Friendly reminder to landowners. There's a CRP CP31 bottomland timber establishment on prairies. It's a continuous sign-up practice as voluntary conservation on 100-year floodplains in the cropped areas. Okay, too many are coming in. Is there a possibility to create a floodplain in land where the stream is a channel that is cut fairly deep, so fairly incised?
Yeah, I think there'd be some probably some construction work involved to try and kind of get that reconnected at some level, but you're just dealing with elevations and topography at that point. And, unless you back the water up to intersect it, you're kind of high and dry for a little bit. Rivers will want to eventually carve a new floodplain, but honestly, it's probably not in our lifetime that will happen, but it will eventually carve a new floodplain in, within that area of incision.
Okay, here's another one. Do you know the area of restored floodplains in Iowa or broader Midwestern Corn Belt as compared to the farmed floodplains?
No, but that's a great question. If so, whoever asked that has insight into that. I would like to hear that.
Another one, is it possible deep-rooted cover crops in conjunction with row crops actually exacerbate nutrient movement into the water table?
Yeah, I don't know. I would have a hard time seeing it exacerbate. I think it would, at some level start pulling out some of that stored nutrient that may have been lost during the cropping period, but probably not going to go far down this line until I give it some more thought.
Any apparent reason why oxbows are more chemically effective than bioreactors or saturated buffers for nutrient reduction?
Well, I'm not sure that I would call them, the nutrient reductions we see in these oxbows are really comparable. It's just, in terms of bioreactors and saturated buffers at 50% reduction, and bioreactors are 40, 50%, and same with oxbows. So they're all taking kind of field level nitrate loads, removing it about half. I think with the advantage of the oxbows, to sell them a little bit, would be all the other ecosystem services that you get with oxbows. They're not buried beneath the ground. Who doesn't want some fish and wildlife usage of these systems? So I think the advantage of the oxbows compared to those other strategies is not necessarily the nitrate reductions, it's more the ecosystem services that they provide in addition to that nitrate reduction.
Here's one I think could be really interesting. So the conversion of alluvial cropland to perennial vegetation would open thousands of acres in Iowa to grazing opportunities. What effect would you expect grazing animals to have on the hydrology and nutrient reduction of these alluvial areas?
Great question. I think provided you manage the herd size and rotationally graze or manage vegetation, I think it could work very well. I mean, you want to keep them out of the stream, keep them from beating down the stream banks and contributing to phosphorus loss, and provide them some water. But I mean, after the 2008 flood at the Nature Conservancy Swamp White Oak, they had a massive influx of reed canary grass, and it changed the character there after that flood. And the TNC has since worked with a local producer to bring in cattle and graze that area to keep down some of the non-native invasives that have come in. Not to just using them as an example, but I think there's really a place where grazing can coexist with floodplains very well. In fact, in this case, it was used as it's still being used as kind of a restoration strategy.
Yeah, I think that sounds really interesting. Okay, so another one, in your opinion, well, you might want to stay away from these. I don't know, the more policy, but in your opinion, is the low-hanging fruit policy change regarding crop insurance and CRP? As a very non-informed 30,000-foot person on this topic, I think it's, I'm going to go out on a limb. I think that's a big deal. If you remove kind of the insurance and the indemnification of this, let the buyer beware here. Like, if you want to crop it, you're going to lose your crop on a 2-year floodplain, say on average 1 every 2 years. If that's a risk you're willing to take, feel free, but we're not going to pay you for it. And I would think there might be alternative uses for that land as opposed to the risk associated with cropping these low environments. And that kind of gets at thinking back to the previous question about the grazing, and there's another question in here kind of thinking about the thoughts on perennial crops, nut trees, prescriptive grazing in these areas as still a productive land, or still utilizing that land in some way, but in a way that still might provide some of the hydrologic and nutrient reduction benefits that you've been able to quantify with different land uses.
Yeah, I agree completely. So I'm not saying don't use it, maybe just not use it for that purpose that has some real risks associated with it.
I know there are a couple questions we didn't get to, but I think in the interest of time, we will keep it there. And Keith, I just want to thank you very much for another excellent presentation. Really appreciate your willingness to get on and start off 2023 on such a great note and something to really think about. One of these years, we're going to have more water in our floodplains, right? And so, you know, let's be prepared to think about that a little differently. The last couple of years, we've not had much in many areas, but we've been in Iowa long enough to know that we will. Last plug, if you need a CCA CEU, email Alena Whitaker, ALENAW @iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. With that, I'll give Keith the last parting shot.
Well, thanks for the opportunity. Reach out if you have any questions. And again, sorry for the whirlwind tour through this. There's a lot to get through. And if you have any questions about any one thing, there's probably been a study or a paper written on it. So I can be happy to provide any extra information.
Thanks, Keith.